Good afternoon, good morning, good evening, whatever it might be. To my calculus students, I know this is not going to seem like this for you because you've been watching these every day, but it's been a long time since I've seen you in this way because I took a little break from videos and now I'm back. Anyway, section 6.1 today, antiderivatives. So we touched briefly on antiderivatives back in chapter 5. We just gave you the basic idea of an antiderivative. Oops, let me get to the correct page here. Sorry. So we use a big F, which I'll show you in a second. So the basic idea of an antiderivative is working backwards. So we have a new symbol here for you. It's this little symbol right here, which you've probably seen before. It's called an integral symbol. I'm going to kind of introduce it to you again in just a second. Get rid of that for you. So the idea is if you take small f, and you take the integral or antiderivative, those terms are synonymous right now, we get what we call big F of x plus c. So we've done a couple of those in chapter 5. So the integral of small f equals big F, meaning big F prime equals small f. We're just working backwards, or it's called antiderivative, okay? Let me give you some words here. This thing right here is actually called an integral symbol or an integral sign. This thing inside the integral is called an integrand. Just so you know the words, there's usually a dx here because that's telling us which variable we originally took the derivative with respect to. It's not super important. I'm going to be honest with you. Sometimes I forget it. It's kind of important for sure. We'll talk more about it later, why it's important. This is called an indefinite integral. Later on, we're going to do things that are called definite integrals. And then we're going to make the connections between the two. So right now, it's basically finding antiderivatives. So like a very basic problem might be a very simple power rule. We did some power rules back in chapter 5. If you want to take the antiderivative of x to the n, you're going to get x to the n plus 1 over n plus 1. And then remember, we just tack on this plus c to every problem because the derivative of a constant is 0. So when we take that derivative, we can wind up back where we were. So if we got an ant like this, x cubed dx, this is going to be x to the 4th over 4. And again, like I mentioned in chapter 5, the cool thing about derivatives is you can always check your work. Sorry, plus c. You can check your work. You just take the derivative of x to the 4th, which is 4x cubed. That 4 is just a constant. And you get x cubed. Just get a little quick check back to where we were. This does not work if n is 1. I'll show you why real quick. If n is 1, it's x to the negative 1. And if you apply this rule, you add 1, so you get x to the 0 over 0. We got a problem. All right. So this rule only works for powers other than a negative 1. You should know that one, though. By the way, I'm going to bring up some more in just a second. The next question I'm actually going to ask you is how many others should you know other than the power rule? So now we have a power rule. How many others? If you think about this one, I'll rewrite this for you. Remember, x to the negative 1 is the same thing as 1 over x. So you should know what the antiderivative of 1 over x is. It's natural log of x because the derivative of natural log of x is 1 over x. Right, so that's what I mean. How many others should you know? So you should know things like the trig function. So you should know this, secant x, tangent x. That's going to be a secant x. Sorry, I forgot the plus c up there also. So any of the ones that we've done that are like what I call one-step ones. So all the trig functions, those 6, the secant sine, cosine, secant tangent, secant squared, those you should know. You should also know the exponentials. We can just work backwards. You should also know the logarithms. You can just work backwards. So I'm not going to do those examples. I'm going to leave those for you in the homework. You can check the book if you want. But anything, this homework assignment tonight, the first time should be pretty quick because they're just like one step. We're going to learn how to take antiderivatives of everything. But right now, it's just the ones that like the memorized rules. So, here's another example. You should probably know what the antiderivative of 1 over 1 plus x squared is, and that's tangent inverse of x. So you should know the inverse trig functions also because the derivative of tangent is 1 over 1 plus x squared. Okay? So that's the basic idea of antiderivatives. Tonight's just going to practice a lot of the ones that kind of memorize skills. The homework assignment should be relatively quick, I hope, because it's either kind of you know it or you don't. You might have to do a little reasoning and thinking, but there's not a lot of tricky things yet. We're going to have a lot of methods to do later but not quite yet. So then I just got some other little facts that are pretty straightforward. This is saying the antiderivative of the derivative of f. Okay, so this is going to be just f of x plus c. Think about this. If you got some function here, this tells you to take the derivative of it, right? So you take the derivative of it, you get some other function. I don't know what it is, but you get something. And then that symbol tells you to take the antiderivative of it. And then you're right back to where you started, right? So antiderivative, derivative are undoing each other. So when you're being asked to do both like this, you end up right back where you started. However, since we did the antiderivative second order of operations, we do inside first, we get this plus c at the end. This one, you take the antiderivative of f first, which gives you big F, and then you take the derivative of big F, and you get small f, so we're right back to where we started. Notice the difference between those two. Because we did the integral first on the first one, there's a plus c. However, we did the integral second in the first one, so we got the plus c, and then the second one, we did the derivative second, so there's no plus c because that plus c disappears. When you take the antiderivative, you get the plus c. This is like d dx of big F of x plus c, right? Because the antiderivative of small f is big F. Now you take the derivative, you're back to f of x. All right? And then the last thing, I got a couple example problems for you. I'm not going to do them. I'll just kind of point out you got some power rules. In this second one there, the only way to do this one, I will do this, kind of start you on this one, is we don't have ways to do these other things yet. We're going to have chain rules and product rules and quotient rules, kind of working backwards. But right now, we're kind of back to the beginning. All you can do is multiply this out, x to the fourth plus 2x squared plus 1 over x squared, and then break it up. X squared plus 2 plus 1 over x squared. Now you got, in essence, 3 different power rules. So you just do these things. And the last little thing is really the same thing, but these are called differential equations. If you are so inclined to take some more math after this class, go to college and take some math. I know you'll probably take multivariable calculus next, but the course after that is typically called differential equations, actually an entire course. A differential equation, I'm not going to write this down so much, just want to write it down. A differential equation is any equation that has some derivative in it, first derivative, second derivative, third derivative. It just has some derivative in it, and they're going to ask you to solve it. So I have 2 different examples here, so I'm going to, let's do this. There's 2 different ones, so I'm just going to do one of them for now. So let me get rid of this one. So here's just a little example of a differential equation. It's the most basic type. It's f prime of x equals 6x squared plus x minus 5. And then this is called an initial condition. They tell you that when x is 0, y is 2. So all a differential equation is, when you solve a differential equation, just by definition, you're like, what do I solve for? It says f prime of x equals 6x squared plus x minus 5. You're solving for y. And remember, f prime is just y prime, right? So basically, you're going to get a derivative, and then you have to find the function. So it's really the same thing as an antiderivative. However, they're not all that simple. Right now they are, so it's just really the same thing. It's just a different terminology. But later on, some of the differential equations we deal with will be a little more complicated. So you start with y by just taking the antiderivative. So you get 6x cubed. I like to do this just so you can see it. 6x cubed over 3 plus x squared over 2 minus 5x plus c. Just straight application of 3 power rules. And then the constant. We have an initial condition when x is 0, y is 2. So 2 equals 0 plus 0 minus 0 plus c. So c is 2. Now we can go back and just say y equals 2x cubed plus 1/2 x squared. Any form is fine. Minus 5x plus 2. And there's my answer to my question. So my other example, which I'm not going to do, you might notice was a second derivative, actually. You just have to work backwards twice. So it's just more practice in finding antiderivatives, which is the big chunk of your homework tonight. There should be kind of one step. We could have done this last chapter when we introduced it to you, but they just threw the term at you. Now we're going to dig a little deeper, and then we'll learn other ways to find more derivatives as we go through this chapter. So that's it for 6-1.